Okay, good afternoon, everyone. Welcome to ISPE's Virtual Bootcamp webinar. Today's topic is Design and Building with Geopier Elements, presented by Brett Zitny. My name is Ariana. I'm an Education Specialist with ISP. I'll also be today's moderator. So as always, if you have any questions about today's program or any of our other programs, please reach out to me and I'll be happy to help you. Just have a few quick announcements. As a reminder, we will not have handouts for this presentation, but you can find the link to the quiz on the same web page as past few weeks. You should have received that link in your confirmation email from this morning. I'll also go ahead and drop that link in the chat box here so you guys can view that. You should have, let's see here. Oh, just please complete the quiz by this Friday so I can get out PDA certificates as soon as possible. About questions, we are going to be reaching a few natural stopping points during today's presentation where Brett will ask any of you to type in any questions that you have. So I'll read those aloud as we go, but we'll also be saving some time at the end for any additional questions. I think that's all I have, so I'll hand it over to Brett.
All right, thanks so much, Ariana. And just a quick audio check. If anyone can't hear me, please type in the box. Ariana is moderating that throughout the discussion today. But thanks so much for joining us this afternoon. My name is Brett Zitny. I'm a region engineer with Geopier Foundation Company, and pleased to be here with you all today to talk about ground improvement, and specifically how we select ground improvement systems for the projects we're considering, and then once selected, how we move forward into designing those systems, and really what design considerations are important for ground improvements. As far as me specifically, your presenter, I come from a design build background in geotechnical contracting. Now working with Geopier, I focus exclusively on ground improvement, and I work primarily in Illinois and Eastern Missouri, but I'm based up in the Chicagoland area. So seeing as this is the SC Bootcamp, I've included a number of slides and references on design and calculations, in addition to the typical information on ground improvement systems and selecting the appropriate methods for soil conditions that we might see. So I'm confident that there will be something here appealing for everybody, and we'll all be able to walk away with something from our talk today. So as far as the format, Ariana, I think, handled that. We will be stopping a couple points throughout, and you'll be able to type in any questions you may have if you want to take note of those throughout the talk, and we can address those once we get there. So today, like I mentioned, we'll be covering a range of topics, and what I'd like to start with is talking briefly about the timeline of progression of ground improvement, really in terms of where we started in the industry and where we are today. And what I hope many of you will realize is that there really is a significant amount of innovation in the ground improvement market. A lot changes year to year, and we're really continually innovating to bring new applications to the market to solve challenging soil conditions. So we'll start by having a brief discussion on historical ground improvement techniques, and then move into the current applications that we're using on the majority of the problems that we're seeing in today's age. And those are techniques would be rammed aggregate piers and rigid inclusions. So we'll spend the bulk of our time talking about those two techniques today, as far as selecting the appropriate techniques themselves, and then also the design parameters as well. And then we'll move on into quality control methods for these applications and the procedures and tests we run to verify that they're installed correctly. And at the end there, I've got a couple optional topics. I plan to go about 50 minutes, and I think we'll probably have time for maybe slope stability, and for any folks who are down further south near St. Louis, we can talk a little bit about liquefaction as well. So to start our talk, I'd just like to take a quick step back in history and talk some about where we started before ground improvement applications really took off for the intermediate foundation market. And really, it wasn't that long ago. We really only had 3 foundation support options, really about 30 years ago. So we had our lightly loaded buildings, which would be supported by spread footings. And then we had our high-rise or heavily loaded structures, which would almost always be founded on deep foundations. And then we had kind of that nuisance group in the middle, the medium buildings, or the intermediate group, as we might call it. And those might be 2, 3, maybe 5-story buildings. They might have basements, they might have costly undercuts, or they may have just been put on full-blown defoundation because there really weren't many other options at the time. And so prior to the commercial ground improvement market coming into existence, there really was a very strong need for an alternative to this middle group here, where people encountered soils issues and needed to support their structures in a more cost-effective fashion. And that need started to be satisfied around the time that ground improvement techniques were introduced to the intermediate foundation market. And this was really in the early 90s. And right around this time, there was finally a cost-effective way to support these moderately loaded structures in a fashion which didn't require costly defoundations or over-excavation. And initially, this took the form of rammed aggregate piers, the installation of which is pictured on the right there. And really one of the first techniques or products designed to provide ground improvement in a cost-effective fashion to support these structures. And we've got a couple renditions here on the screen. On the left there, that's an early rendition, probably the late 80s when this was being developed, being done off a skid steer. But thankfully today, we're a little more refined. We do these off of track excavators with high energy tampers. So we have come a long way in the last 30 years. And fast forwarding 30 years to today, the present day, where do we see ground improvement technologies being applied? And really the answer is everywhere. The intermediate foundation market, as many of us probably think of it, involves the support of buildings in terms of foundations and floor slabs for pretty much any type of building imaginable. And now normally there's an upper limit to the size of buildings which we're supporting. We're typically not supporting high-rises in downtown Chicago or St. Louis, for example. But we are seeing structures of increasingly larger size and loads, sometimes over 10 stories in some cases, being supported by ground improvement. Transportation structures, embankments, MSC walls, often demanding bearing pressures on the order of 3 to 5 KSF in many instances. And something we're running into quite a bit of here in Illinois, tanks and grain bins, and particularly the latter. And these are challenging structures, to say the least, with bearing pressures typically between, or bearing pressure demands typically between 4 and 6 KSF. And in some cases, depending on what the needs are, they can have fairly demanding settlement requirements. Then in terms of industrial and energy applications, wind turbines, we're seeing more and more of these in Illinois. And the industrial sector, which is broadly defined, but may include warehouses and refineries. And as I mentioned, we'll talk some about liquefaction mitigation at the end there for those of you who may practice down further south near St. Louis. And finally, in addition to the bearing properties of the site we're improving, we also have capabilities to provide uplift and lateral resistance as well where needed. So why ground improvement? Why not put everything on piles? And to answer that, we normally see ground improvement as the alternative between shallow foundations where soils are reasonably competent and deep foundation systems where soils may be very poor or the loads may be very high. And also where we aren't able to use an economical shallow foundation either on natural soil or after over-excavation. So intermediate foundation systems are often the system of choice for these situations in terms of economy and performance. And one application where we do see quite a bit of in urban areas such as Chicago, St. Louis, probably where many of us practice, is a more economical approach to supporting structures in areas with large amounts of undocumented fill. And when we do investigations for these sites, we'll do a certain number of borings. Maybe we'll sample 0.01% of the site. And the fill may even seem reasonable based on whatever that small percentage of the site we document through our borings. But really, as we all know, it's the risk of the other 99.9% of the site that's a challenge. And we can have buried debris, organics, materials that could break down over time and cause issues for the structure that it's supporting. And the risk of having that occur due to undocumented fill is almost always unacceptable to most owners and project teams. And that makes ground improvement a positive option for mitigating those risks. So to start our talk on specific techniques and applications, we'll chat some about rammed aggregate piers. So rammed aggregate piers are the system we use to support the large majority of structures in the intermediate foundation market. I'm just gonna turn on my laser pointer here. There we go. So the way these are installed, and this really is the modern version of what really began the commercial ground improvement system back in the early 90s, is, first we're drilling a cavity, and I guess I should preface this. This is one of several techniques. This is what we call our GP3, or our open hole top fed rammed aggregate pier. So what we do is we start by drilling the appropriately sized element, and these are normally 18 to 36 inches. So I'll drill that down to whatever target installation depth we're trying to get to. So if we're trying to get through undocumented fill or get through a loose sand, soft clay, whatever it might be, we're drilling down to get to our more competent layer. Then we'll introduce stone into that cavity, usually a CA6 or CA7 type stone, into thin lifts, 1 to 2 foot lifts normally. And then we'll come in with our high energy tamper, which is shown here off of a track excavator, and we'll tamp that material, again in 1 to 2 foot lifts, and build that element, that rammed aggregate pier, up to the surface. And that tamping action is twofold. So, one, we're compacting the aggregate introduced into the hole, and that's providing or building our stiffened element. And two, we're forcing the aggregate radially out into the soil as well, and that's going to provide an improvement factor to the surrounding soil. So by installing a system of these elements beneath the foundation, a slab, MSC wall, or embankment, whatever it might be that we're supporting, we're not only providing a stiffened element to attract the load of the structure, but we're also improving the surrounding soil as well. And this is a typical crew setup for a top-fed system, a drill and fill system. So we have our pre-drill rig out in front here, which is drilling those 18 to 36 inch diameter elements. And then we'll have our tamping rig following behind with a skid steer funneling stone to and from the hole as we build these 1 to 2 foot lifts of stone up to the surface. I've got a quick video to show of what this looks like. So I'm not sure if there's audio on everyone's computer. It may be a little loud, just to warn you. So what we see here is we've got our pre-drill rig over to the left, and you can see this is excavating out that cavity, maybe a 30-inch element. And then our tamping rig is over here to the side with the skid steer that's funneling stone to and from the cavity to build these elements. So he's just completed a lift, and then we're introducing the aggregate, so probably a CA7 type stone, and then we'll trip down back into the hole and compact the next lift of aggregate. And the depth of these elements will vary. They can go 10, 20, 30 feet, sometimes deeper. And we'll start from the bottom and just build our way all the way up to the top, as we're going to see here in this schematic. So we'll first compact our bottom bulb, as we call it, and then continue all the way up to the surface in those 1 to 2 foot lifts. And I think you guys get the picture. I probably don't need to watch the whole thing here. And initially, when we started doing these techniques in the early 90s, primarily in cohesive soils with reasonable strength, the thought was we could take a site with something like 3,000 PSF bearing and maybe bring it up to 4,500 PSF, bring some value that way. Today, what we're seeing with rammed aggregate pier technologies is, we're typically providing allowable bearing pressures on the order of 4 to 6 KSF, and sometimes as high as 7 KSF in the right soil conditions. And these elements installed very well in clay soils, soils where we don't have too many concerns about the water table. But when we do look beyond the narrow scope of, kind of those specific soil conditions, we can see that there is a lot still that needs to be addressed. And as we've expanded our operational capabilities, we're addressing many soil conditions beyond that. We're addressing peats, organic material, soft clays, and we're also installing these elements in high water tables as well. And when we're dealing with collapsible soils, such as in sands, or if we're dealing with a very high water table as well, you might be asking yourself, well, what do we do in that instance? And in those cases, what we're doing is we're going to be installing a displacement element. So going with a displacement system, which is pictured here, essentially what we're doing is we're building a similarly sized element, though the installation sequence is slightly different. So instead of pre-drilling a cavity, which then will feed stone from the top, in this instance, what we'll do is we'll drive a mandrel to whatever installation that we're trying to get to. And then we'll introduce stone into the mandrel with the hopper at the top here of the mandrel. The stone will flow down to the tip, and then we'll continue building that element in a similar fashion up to the surface. The same benefits as the drill and fill system, but just a different way to do it to allow us to get a little deeper, as well as to avoid some of the limitations of a hole staying open, or avoid limitations of working in collapsible soils as well. So how does it work? I talked some about the operational end of it, and you might be thinking, oh, this is great. We just show up, dump some stone on the ground, and everyone's problems go away, right? Well, there actually is quite a bit of design and design methodology that goes into these, and making sure that these are put together appropriately. And normally when we're talking about ground improvements, there's usually three things that we're trying to improve. So settlement is the first and probably the biggest one, what normally controls. The second's allowable bearing capacity, and improving the allowable bearing capacity of the site. And I mentioned that's normally somewhere in the range of 4 to 6 KSF, but can be as high as 7 KSF in the right soil conditions. And also global stability, if we're dealing with embankments or MSE walls, or if something's built on a slope, making sure that there's an adequate factor of safety for global stability. So, like I mentioned, for building work particularly, settlement is almost always going to control. We're typically controlling the 1 inch total, half-inch differential. If there are tighter requirements, we just need to know that, and we have to design for that. But as we get into industrial structures as well, something else to think about is, we do see some yielding problems in some instances, and maybe even some bearing capacity issues. But often settlement is the driving criteria 99% of the time. So in the case of settlement, our basic design methodology involves looking at a stiffened upper zone, and that's essentially where we're improving the soils by installing a system of Geopier elements. And the thought is that we're creating an engineered crust, which is then going to increase the composite strength of the soil, and then we'll also in turn control the settlement. And then we'll look at it two ways. So we have the upper zone where we improve, and we also have the lower zone beneath the piers that we install, which is unimproved. And the idea is that each Geopier element which is installed acts as a stiffened element in a weaker matrix of soils, or a spring. And that stiffened element's going to attract more load and increase the load carrying capacity of the site, or increase the composite properties of the site. And we'll calculate settlement primarily by looking at the composite modulus of the upper zone of the site that we've improved. So to do this, we consider the area replacement ratio, or the ratio of piers to the in situ soil on site. And typical area replacement ratios are normally 10% to, in some cases, as high as 30% on the very high end. And what we do is we take the modulus of the pier and the surrounding soil, and we'll calculate the composite modulus of our upper zone, which we then use to calculate the anticipated settlements of the upper zone. And we'll come up with moduli of the existing soil, the in situ soil, using conventional geotechnical correlations. So SPT tests, CPT correlations, probably many of those which you use today in practice. And then the modulus of the pier, the rammed aggregate pier, is from our own internal data from testing that we've done over the years of rammed aggregate pier elements in various soil conditions. So thinking about these two items, stiffness of the pier itself and the soil, we're normally something on the order of 7 to 10 as a ballpark ratio of the stiffness of the pier to the soil itself. And because of that, the way we design these elements is we design the pier, or I should say that the foundation bears directly on the pier, and we design assuming that's going to move forward. So we don't need to have a load transfer platform or anything beneath the foundation in the majority of instances to transfer load, because the relative stiffness is only something on the order of 7 to 10, we don't require that, and we're able to have the foundation bear directly on the Geopier element. So that's the upper zone portion. After coming up with the settlement calculation, then we'll look at the lower zone beneath our Geopier elements, which is the second component of our analysis. And this is done using a conventional geotechnical settlement analysis. So we'll calculate it using moduli or compressibility parameters for clay soils, if that's what we're dealing with. And then the settlement of the improved zone is the sum of the two. So when we're looking at the lower zone, this honestly is where good geotechnical data from a site investigation comes into play. And if we're dealing with fine-grained soils or clay soils, making sure we get some good compression tests, and at depth, compression tests at depth, not necessarily 5 feet from the surface, which give us good recompression and virgin compression curves as well. And we rely heavily on that information to calculate settlement estimates. And we'll confirm all these design assumptions and methodologies on site during construction with a modulus test. And this is where we're going to measure the pier stiffness of the element once installed. And we'll talk more about this in more detail later on. But as a company, we have records of many tests we've performed over the last few decades in quite a few different soil conditions. And being geotechnical engineers, we calculate these out to the third or fourth decimal place, right? No, it's a joke. I'm sure if you're familiar with the practice, you're aware of the range of what's reasonable in geotechnical engineering, but we're able to be fairly accurate with what our settlement estimates are based on our data. So in summary, both lower zone and upper zone settlement are important in coming up with the estimated settlement for the system as a whole. And what we do on a specific level is, we'll modify our area replacement ratio or increase the shaft length to make sure that we're controlling our settlement appropriately. And we'll confirm our assumptions in the field with the modulus test. And again, the lengths can be modified to reach an appropriate layer or adjust the settlement appropriately. And as I mentioned, lower zone compressibility is very important, and we rely very heavily on that and having good data to make sure that we have a proper design. So with that, I'd like to pause for 20, 30 seconds, see if anyone has any questions, if anyone would like to type anything in at this point. And if not, we'll just move on, but I'll wait to see if Ariana has anything for us.
Looks like we don't have any questions currently, but like you said, if you want to take this time to type them in, I'll keep on the lookout. All right, looks like we have none so far.
Okay, and no worries there. We'll also have some time at the end. So moving forward into rigid inclusions, our next topic. So while we've used rammed aggregate pier technology for years, and they are used still for supporting a wide variety of structures, they're not always the best ground improvement option, particularly when we're dealing with challenging sites. And for that reason, ground improvement systems have evolved to include rigid inclusion systems to fill this need for challenging sites. And when I say challenging sites, there's a couple of things in particular I'm thinking about. So if let me get rid of this laser pointer here. It's kind of annoying. So if we're dealing with particularly soft soils or organics, so if we're in weight of hammer clays or organics, and we have a deposit of these materials, which are over a competent layer, like if we're over rock or over soil, which is particularly applicable for areas such as near St. Louis, where rock can be very shallow. In these instances, a standard aggregate pier really isn't able to be used. Because of that, it's an element which relies very heavily on confinement. And if we're in zero below count clays or organics, particularly in organics, over time we're at risk of degradation of that surrounding soil, and as a result, stiffness of the element is going to degrade over time, and an aggregate pier isn't really going to be able to provide that load carrying capacity for long term. And that's not always the case if loads are very light. If it's a one-story building, if it's a Dollar General or something, and we're looking at 25 to 50 kip column loads, that may not necessarily be an issue depending on the water contents, but it's definitely something to think about. Another point is higher loaded buildings or embankment loads. And when we're talking about aggregate piers, these elements can sometimes carry at times over 100 kips or more per element. But if we're in far excess of a demand, if we're in far excess of numbers like this, a rigid inclusion system, a stiffer system, may be the solution to use to have higher load carrying capacity elements. And the same can be said for floor slabs. If we're dealing with heavy rack loads or heavy industrial loads, a rigid inclusion system may be appropriate depending on what the loading conditions are. And essentially, when I say rigid inclusions, I'm essentially referring to ground improvement elements with a cementitious component. And by adding that cementitious component to the elements, we're increasing their stiffness as well as their strength, and also allowing them to be used in problematic soils or where there are structures with higher loads that we have to deal with as well, as I mentioned. And as I mentioned, they're really the system of choice when we're dealing with organics or very soft soils. So like aggregate piers, rigid inclusions are not structurally connected to the structure they're supporting. Well, I guess I talked some about the fact that we don't need a load transfer platform, but I guess I didn't mention that the aggregate pier itself is strictly a soil reinforcement system. So there's no structural connection whatsoever to the footing or whatever it's supporting. And the same can be said for rigid inclusions. But when we are talking about rigid inclusions, because of the relative stiffness between these elements, between RIs and the ground, there is a need for a load transfer platform to distribute the load from the foundation or whatever we're supporting adequately to the piers. And that relative stiffness may be something on the order of 300 to 500, which is why this is needed. And because of that, the rigid inclusion is going to attract the entirety of the load beneath the structure, and that's why we need that load transfer platform to allow stress arching to the elements. So these are constructed in various forms, but like I mentioned, they all feature a cementitious or a rigid component to them. And while rammed aggregate piers don't necessarily need what we might think of as a firm bearing layer, these elements, rigid inclusions, will transfer load. And so we are looking for a competent bearing layer to carry that load from wherever we're supporting. And we talked some about organics already and higher load carrying capacity. The bearing pressures that we're able to provide are higher as well for rigid inclusion systems. So rammed aggregate piers 4 to 7 KSF, RIs might be 8 KSF to 10 KSF, 10 KSF, and depending on the soil conditions, we might even be able to go a little bit higher. And here's some of the equipment associated with the install of one of these systems. So we have our large mast rig on the left here. And then the way these are installed is we have kind of like our displacement aggregate pier. We have a mandrel, which is going to be driven to whatever our insulation depth is, wherever that bearing layer is. And then we have, we'll have a pump on site. We'll either batch the grout that we're going to pump through the mandrel on site, or we'll have ready mix delivered. And that material is pumped up to the top of the mandrel, which is then flows down to the tip, and we'll build our elements from the bottom up. And this is a kind of a schematic of that process, fairly self-explanatory. But one thing worth noting is one thing we are able to do with the system is once we drive to whatever our bearing depth is, we're able to build a bottom bulb, so a larger diameter area where these elements are going to bear on the appropriate layer. And that provides a couple of benefits to the system. So, these might be 12 to 18-inch diameter elements. Then what we do is we'll build a bulb, which is maybe another foot in diameter at the bottom, and since these are end-bearing elements, we're able to increase the load carrying capacity of these versus, something like an aggregate pile or some other type of system, which may not necessarily have that benefit. So it's one thing we're able to do in addition. And here's a couple of pictures of what that installation would look like on a job site. So here's our high-mast rig. We've got looks like they're delivering ready mix here into a concrete pump, which is then pumping this up into the mandrel. And this excavator is here probably just for support, for maybe spoil management or just getting things ready for the rest of the install. And this is another view of that high mast rig being prepared to drive to depth. So you've got another video for us to see. So there's a shot of the rig, and right here is where they're beginning to drive to depth. And then another schematic of what this looks like. So that green is basically intended to represent an organic or some type of weak layer. Then maybe we're getting down to a layer of some good till, and we'll build our bottom bulb, do a couple of lifts of that, and then we'll build our element up to the surface, and our foundations will bear on the elements above the load transfer platform. So that talks some about the operational considerations, how these are installed. Now we'll talk some about the design methodology we use in coming up with designs for rigid inclusions. And when we're talking, we talked about aggregate piers. Really, in the case of aggregate piers, we're strictly concerned about the geotechnical capacity of the element. But in the case of rigid inclusions, a high stiffness element, we also have to consider the structural component of the element as well. And whether we're using LRFD or ASD, however we're going forward with our structural design, the capacity is going to be a function of the size as well as the compressive strength of the element. And our strength reduction factor is normally between 0.3 and 0.55. So for ASD, we might use a higher phi value for IBC, and that's if we perform a load test and there's adequate geotechnical information. And beyond that, we also will drop the diameter of the element in our calculations down by about an inch or two, and that's to account for squeeze effects which occur during the installation and may decrease the diameter of the elements. And geotechnically, we're considering two components of the element. So the first of those is skin friction, and that's simply a function of the surface area of the pier, which actually we'll use sparingly in calculating resistance. And the reason for that is typically, we're using these elements, we're supporting structures through fill and very soft materials. And because of that, we really can't rely on any adequate skin friction resistance in the majority of cases. There are some instances, though, where we may have a reasonably competent layer above the bearing elevation, and considering that, we may take some component of skin friction in calculating our resistance for the rigid inclusion, but typically we're not able to do that. And our end bearing component, which is really where we get the majority of our capacity for elements such as these. So here we're calculating a unit end bearing resistance, in this case for cohesionless soils, and then we'll select our alpha coefficient and bearing capacity factor based on the friction angle of the bearing layer. And for cohesive soils, if we're looking at supporting these in cohesive soils, we'll consider the undrained shear strength for undrained loading, as well as the drain cohesion and bearing capacity factors for drain loading. And normally we're considering both as far as trying to determine what the controlling resistance will be. The capacities we're normally dealing with are somewhere on the order of 100 to 200 kips, sometimes higher, but normally in that range. So once we've determined our allowable capacity per element, the next step is, similar to aggregate piers, we need to determine what our element spacing is going to be and our replacement ratio to meet our settlement requirements. And with one difference between aggregate piers and rigid inclusion elements is we're considering 3 components to that settlement analysis, as opposed to aggregate piers where we're just looking at the upper zone and the lower zone. And that third element is our engineered pad, our load transfer platform, which is above the elements and beneath the foundation. So that's that third component that we have to consider in designing for settlement. And the rest is the similar concept. We have our upper zone of the piers, and then the lower zone, which is unimproved. So we'll look at that 3 different ways. We'll consider elastic settlement within the engineered gravel pad layer, and then we'll consider similar to aggregate piers, we'll consider a spring analogy to determine the reinforced zone settlement, the upper zone settlement. And then the lower zone beneath the rigid inclusions is analyzed conventionally, looking at stress transfer down to the bearing layer, and either consolidation or consolidation settlement for cohesive soils, or elastic behavior for granular materials. And then the settlement of the structure, whatever we're supporting, is the sum of the 3. So looking at the gravel pad, the load transfer platform, we're often looking at moduli in the 300 to 750 KSF range. And, heights may vary between 8 to 12 inches typically. And for whatever reason, I keep saying gravel pad, but I mean, they can be mud mats. They can be a combination. It can be a stone pad with the mud mat on top. There could be geogrids in there. There's a wide variety of ways that we can put these together to transfer the stress from the foundation adequately down to the top of the elements. And we've seen traditionally these will settle somewhere on the order of a 1/4 inch, maybe a little more, and that's really based on field tests. And then the reinforced zone itself, similar to aggregate piers, we're considering the stiffness of the element. Here we're referring to as kg, as well as the stiffness of the native material, or km. And we'll use those 2 relative stiffnesses to come up with our settlement estimates. And we'll use those in the area replacement ratio, or I should say in terms of coming up with the area replacement ratio that we need for the site. And we'll use all that to come up with the design stress of the piers in calculating the settlement. And the relative stiffness, as I mentioned, between the elements is somewhere in the 300s typically. And the settlements will be on the order of maybe a 1/4 to 1/2 inch in that upper zone area. And since these are end-bearing elements, I mentioned we'll look at stress transfer down to the termination layer, wherever we're building these elements to, and we'll use conventional methods such as elastic or consolidation calculations to determine the lower zone settlement. So it's a similar concept to aggregate piers, just as far as the fact that it's a conventional analysis. The only difference is here that we're using stress transfer down to that end-bearing layer, the termination layer. So that wraps up my slides on rigid inclusion, installation, and design. Again, maybe we can just take 30 seconds to see if anyone has any questions. Feel free to type them in.
All right, doesn't look like anyone has any questions so far.
All right, so we'll keep moving on then. So moving forward, we'll talk some about QA/QC and load testing of ground improvement systems. So we've talked about the need for confinement with ground improvement systems and how important that is.
Sorry to interject, Brett. We did get a question come in, if you want to answer that now.
Yeah, absolutely.
How is the soil removed before placing grout with the rigid inclusions? Is it augered out?
So there's, for rigid inclusions, normally we're using a displacement system. And so that would, involve driving our mandrel to whatever installation depth we're supporting. So oftentimes there isn't a need to pre-drill. It's just strict displacement, and that the mandrel will just be driven to whatever depth we're trying to go. Now, in some instances, depending on the loads, if we're talking about for example, a lighter loaded building in organics that have very high water contents, if the loads aren't too high, we might be able to use a drill and fill system, and then use something like cement treated aggregate. So we can use cement treated aggregate, if the depth of the elements doesn't need to be if the elements don't need to go too deep, and that cement treated aggregate, or CTA, that will be built in the same fashion as our drill and fill pier up to the surface, but has a much higher stiffness. So that's one way we might do it with drill and fill, is we might auger it out. But in the majority of cases, we're using a displacement system, and it'll either be entirely cementitious, or we might build what we call a grouted displacement pier. In that instance, we would flood the mandrel with grout and then introduce aggregate and build the aggregate pier as we normally would. So typically it's displacement. All right, I think that was our only question, so we'll keep moving. And please, if you whoever asked the question, if you'd like any follow-up, we'll have another pause at the end, and you're welcome to continue the discussion then. So as I was saying, we rely very heavily on confinement, particularly in the case of aggregate piers. And we also showed that we see an improvement factor of the surrounding soils, and that's due to the ramming action of the tamper forcing the aggregate into the surrounding soil. Now with rigid inclusions, as I mentioned just now, I went into a little more detail. Typically those are displacement techniques. And because of that, the improvement usually isn't as dramatic. And often because we're doing these in very poor soils, very soft soils, there quite frankly really isn't much to improve. So in those cases, we're strictly dealing with stress transfer. But at the end of the day, whether it's an aggregate pier or rigid inclusion, we're providing a solution which reinforces the in situ soil and allows standard shallow spread footing construction to occur. So we talked about the fact that we're not structurally connecting any of these two foundation elements. They're simply there to improve the bearing capacity of the in situ soil and control settlements. And I hit on this just briefly earlier, the fact that to confirm our design assumptions, we'll run a load test, or what we call a modulus test. And these do come in various forms, but the preferred method to do it is what we have shown here, which is our single pier modulus test. And what this essentially involves is, on the majority of project sites, we'll install a sacrificial pier for testing for this particular instance. And what we'll do on our test pier is we'll excavate out the top 2 to 3 feet of that pier, and we'll pour a concrete cap, usually with a sonotube. And that cap is intended to represent the footing and how the footing might interact with the aggregate pier. Then we'll have our jacks sit on top of that cap, and we'll build a reaction frame. So we have our beam over here, and we'll have 2 reactions on either end, typically for modulus test. And here the reactions are shown as uplift piers, which we can do, but very often it's more economical to install these with helicals to support the reaction beam. And then with that single pier that we install, we're going to load to about 150% of the design top of pier stress. And it's important to make sure that we're loading the pier to the top of pier stress and not the footing bottom stress, since the former, the top of pier stress, is normally 2 to 3 times larger due to stress concentration because it's a higher stiffness element. And we'll normally locate the test pier in the worst area of the site, or by the worst boring, typically. And we'll measure the resulting deflection at the top of the concrete cap and also at the bottom of the pier using a telltale. So this is a view of that setup. So we've got this is our concrete cap that we've poured. Like I mentioned, we excavate the upper 2 to 3 feet of the pier out, and we'll pour this cap using a sonotube. And then we have a plate which sits on top of the cap, and here's a jack which is going to load the element. And we're measuring displacement in 2 areas. So we have two gauges set up measuring at the plate, and that's essentially capturing the bulging of the element, or the movement of the element in the upper third to half length of the shaft. And then we're also measuring movement at the tip of the element with these two gauges here, which are, you can see, are on these angles, which are affixed to a threaded rod, which is going through this cap here, and then down to a harness at the bottom of the element. And that's telling us what the movement is at the bottom of the pier. And I will come back to that in just a moment. But thinking about that, that gives us two stress strain curves here. And so what we're looking at here is a modulus test result from the data that we come up with. So we have our stress strain curve here, which is the displacement that we measure at the top of the pier, those two gauges that are on the steel plate. And here our design stress is around 19 KSF, and we're running it out to 150%. And then we have our stress strain curve from the bottom of the pier, from those telltales, which are measuring deflection at the bottom of the pier. And this is essentially telling us what we anticipate for probably 99% of the load tests we run on aggregate piers is the majority of the movement at this pier is from bulging in the upper third to half of the shaft length, which is how the majority of these elements fail. If the telltale, the stress strain curve for the telltale were to show quite a bit of displacement, similar to what we would see at the top, then we'd be concerned that these elements are punching through some weak layer at depth, which rarely happens. So typically we're seeing these elements fail in bulging, which is what we're seeing here with the stress strain curve of the movement at the top of the pier. And I'll just go back to a slide here I've got. So those are the results from a modulus test for an aggregate pier. One thing we're also able to do is we're also able to run a full-scale footing load test. And that's what's pictured here. One drawback of a full-scale footing load test is it's about 10 times as expensive, takes significantly longer to install and to run. And also beyond that, what it involves is installing several piers, beneath essentially we build a test footing. Whatever it might be, the largest footing on site, a 10 by 10 footing, we'll reinforce it after we install the piers, and then we load that footing to, in some instances, 1.5 or 2 times whatever the design stress is. And under footing load tests, which are much more expensive and take longer to install, they really don't provide a significant amount of additional information outside of a modulus test, because we're testing group action of piers versus just the response of a single pier under a single modulus test. So we get quite a bit of information running a single modulus test, which is going to return kind of that raw stiffness and tell us whether or not our design assumptions were correct, versus running a full-scale load test, which is going to test pier response of a group of piers. So our preferred method is certainly to run a single modulus load test. Oh, and then this is just one slide here for a load test result for a rigid inclusion. Here our design stress is around 140 KSF, so almost 10 times what we might see for an aggregate pier. And we see a fairly consistent modulus, in this case around 6,000 PCI. And for tests of this nature, we'll normally do a creep test. And here it looks like they held at 115% of the design stress, and then they ran another one at 175%. And we'll also bring it out to twice the design load. And during these creep tests, we'll want to see less than 1/100 of an inch in an hour of movement. So that wraps up rigid inclusions. I'm just going to spend probably another 5 minutes here. I'm going to chat real quick about slope stability and liquefaction mitigation for those of you who may practice down near Southern Illinois. So we talked some about, really exclusively focused on supporting structures and vertical loads. When we're talking about slope stabilization, we've been using ground improvements to improve global stability for some time now. And that's essentially a process of improving the composite properties of the zone within the critical surface to improve the factor of safety against sliding. And when we're talking about shallow slides, or where a failure plane is less than 20 feet from the surface, or where we're simply dealing with seasonal slope creep, like some of these examples which are shown here, another way which we're able to do this is using our SRT, or slope reinforcing technology. And that's a schematic of what this system involves. And this is what these look like. We have let me get my pointer again. So we've got our plate on the end of an angle, or some other element, a pile of some sort, which are driven across the slope, maybe on 5 to 6 foot on centers. And that's providing the shear resistance to the slope, which is having stability issues. So that's what these might look like in schematic. We'll center the plate within whatever unstable layer is having issues, and then drive that tail end of the plate pile into a stable layer beyond to hold back the sliding area. And these are installed using a single piece of equipment, 2 to 3 person crew. They go in pretty quickly, and you know, the installation is designed to be done in challenging access areas. So that's for shallow sliding planes that for 20 feet or less typically. And then our last topic for the day, liquefaction mitigation. And this could easily be an hour-long session on its own. Unfortunately, I've got to whiz through it in just a couple minutes, but I think it's worth talking about since some of us may practice near St. Louis. So as we get near that area, Southern Illinois, St. Louis, we're probably aware that the seismic hazard increases significantly due to the New Madrid fault zone. And you may remember the 2008 Illinois earthquake. You know, I always think of that when I see maps like this. I was a grad student in Illinois at the time, and remember being woken up at 3 or 4 in the morning to, you know, noticeable shaking. Thankfully, that was only a magnitude 5 earthquake, but certainly enough to show that there is a seismic threat, a seismic hazard to this area. And thankfully, something like a magnitude 5 isn't nearly enough to cause liquefaction. And without going into all the specifics of effective stress, the mechanics involved, essentially what we're dealing with liquefaction is that the ground shaking is so severe, it reduces the shear strength of saturated granular deposits to basically nothing. And that causes these saturated deposits to flow as if they're a liquid without any shear resistance. And that's what we see here. This is a picture of Japan in 2011, some loose sand deposits which had flowed to the surface and after their seismic events there. And that might not seem like a big deal if I hadn't said this was Japan. You know, maybe you just look at this and think you need to dig your car out, but no harm, no foul. But then when your structure is relying on that liquefied soil to provide bearing capacity, it can be a huge issue. And because of that, we're required to mitigate against liquefaction potential in seismic areas, such as in Southern Illinois and St. Louis. And we've done this for a time with rammed aggregate piers through densification, the idea being that will lead to overall improvement of the site by adding the dense pier and also providing the improvement factor of the soil as well. And this just may be a pre and post CPT installation plot of you know, what a ground improvement system may be capable of doing in a liquefaction susceptible environment. And we can essentially improve the composite properties of the site, most importantly stiffness and density, to bring the soil to a point where it's deemed to have an adequate resistance to liquefaction. And last slide here. So, you know, we've been blessed in the U.S. to not have had to see the fruits of our labors. As you know, with the exception of Alaska, we really haven't had any major earthquakes or liquefaction events in the continental U.S. for a while now. But I mean, regardless, we're planning for them. But you know, thankfully, we haven't had the misfortune of living through a major seismic event in this area. But one part of the world where we do work, where Geopier works, and you know, unfortunately did go through a fairly serious seismic event was Ecuador in April of 2016. And this was a magnitude 7.8 earthquake. And throughout Ecuador, there were a number of unreinforced bridge embankments which fell victim to soil liquefaction. And this here on the left here is the Mejia bridge embankment, which was not supported by ground improvement in any fashion and suffered liquefaction and then a failure, as you can see. A nearby embankment, which was the Briceño bridge embankment here on the right, was supported by Geopier elements, and there was no major damage to the embankment structures, and the embankment and the bridge were able to stay in service after the seismic event. And we know liquefaction occurred in this general area because of sand boil observations that were seen on site nearby. And so, this is a kind of a final slide, a conclusion, truly is an indication that, as geotechnical engineers, we're getting this right, and we're solving these soil liquefaction problems correctly. I mean, there's still a lot of research, a lot that has to be gained and learned, and quite frankly, and unfortunately, I can't go into too much more for time, and we're in the process of writing a number of papers about this particular earthquake and our observations, but it's ongoing research, and for where we are right now, we're getting the answers correctly. So with that, if there are any more questions, that is the end of my presentation. Thanks so much for attending, and I hope you're all able to pick something up this afternoon.
All right, I'll give you guys a few seconds to type in any last-minute questions while I make some announcements. So first, just a reminder, you can find the link to the quiz in the chat box. You can also find the link in your confirmation email from this morning. Just please complete that by this Friday, and I'll get certificates out as soon as I can. Thank you, Brett, for a great presentation. Thank you to everyone who joined us today. Just reminding everyone, we will be posting this webinar on demand on our website by next week, and October 31st webinar is available as well. So if you know any interested SEs, pass on the word. Our last bootcamp webinar is going to be on November 28th, and that topic is contract pitfalls, presented by Reed Just from Holmes Murphy. We won't be having one next week due to Thanksgiving. We did have one more question come in, so I'll go ahead and ask that. Someone wants to know, what is the largest project Geopier has done?
In terms of, I guess there's a couple components of that, pure size or dollar value. I have to look into that. I mean, we've done quite a few large projects. The big ones that come to mind are the DOT jobs, where we may be supporting, embankments, or, I guess the interesting ones that people always think of are jobs like, we see a lot of these Amazon warehouses, and we've supported quite a few of structures like these, very heavily loaded industrial type structures that may not necessarily be the biggest projects we've done, but certainly many thousands of piers supported, or I should say installed to great depths. But quite honestly, I'm not sure what the largest job is. I'd have to look to see what that might be as far as dollar value or pier count. But I'd say the large ones are in the tens of thousands of piers with depths that may be 30, 40 feet or deeper.
Okay, and it looks like we have one more. When are you required to run a full-scale load test?
When? Yeah, so really the answer should be never. I mean, I guess that's maybe a bad joke, but we would never require a full-scale load test. It's less conservative, and the cost is astronomical. The cost of the project really doesn't justify doing it. It's a nice science experiment. It's fun to install 20 helicals and put in 5 reaction frames and 10 dial gauges and measure how this thing responds, but there's really no benefit to a project. The only requirement we would have to do is whether or not, wherever we're installing these, whatever agency is reviewing our work would require it. And unfortunately, Chicago is one of those places that started requiring multiple full-scale footing load tests on jobs. And, the reality is it just doesn't add value to a project. I mentioned the group effect of measuring the response of multiple piers. And that's fun, it's interesting to see how things respond, but the cost just, in my opinion, just doesn't justify the means to do it. When we run a modulus test, you get a raw indication of the pier stiffness. It's more conservative because it's a single pier. You're not testing group response, and it costs dramatically less. It's 10,000 versus 100,000 or more to run a modulus test versus a full-scale test. So I could talk about that probably for a while and some of the frustrations I've run across in projects, but hopefully that's a short answer.
All right, we haven't had any more questions come in. So again, thank you, Brett. Thank you, everyone else, for being here today. Have a great Wednesday and happy holidays.
All right, thank you very much.